Hello there! Welcome back to our video lecture series about partial differential equations. This one's about the heat equation. Let's begin by asking a question. Suppose that we have a solid object that is warmer in one part than another. How does heat flow through this object? If we assume that the heat will flow in one spatial direction only, we are looking for a function u of x and t, describing the evolution of temperature in the object throughout time. What physics do we need to know in order to formulate an equation of u? Here are some empirical laws of heat conduction that will prove useful. The first quantifies the total quantity of heat, capital Q, in an element of mass m. Q is proportional to the product of the temperature U, the mass m of the element, and the specific heat, gamma, of the material. The second empirical law relates the rate at which heat flows, partial Q, partial T, to the cross-sectional area A through which the heat is flowing. This involves the spatial rate of temperature change, partial U, partial X, and a quantity K known as the thermal conductivity of a material. Next, we take two steps. First, we relate the mass m to the density, cross-sectional area, and distance increment in the direction of flow. Differentiating our heat quantity from the first law gives the expression for the heat flux in the left-hand panel. For the second step, we relate the heat flux to the spatial derivative of temperature over a small differential step delta x, yielding the expression in the right panel. We now have two expressions for partial Q, partial T in terms of the partial derivatives of the temperature U. Finally, we equate these two expressions, yielding an equation in the temperature variable U. The expression on the right-hand side should remind you of the definition of the derivative. Taking a limit as the increment delta x goes to 0, we see that we are left with an equation relating the first derivative of u with respect to t to the second derivative of u with respect to x. This is the heat equation. To keep track of all the physical constants, it is useful to define a quantity, lowercase k, known as the thermal diffusivity. The derivation we just performed generalizes to systems with heat flowing in more than one spatial dimension, since the differential heat flux in the x, y, and z directions can be analyzed separately. The heat equation therefore takes this general form. The upside-down delta squared is a linear partial differential operator known as the Laplacian. It is the sum of the second partial derivatives of all the spatial variables in a system, although generally not in the time variable. The Laplacian generally quantifies an average value of a field over space. It will appear in many or all of the partial differential equations we will study. Let us look at a system modeling a long, thin rod in which temperature can flow only in one spatial dimension, the x direction. We assume the temperature is fixed at some zero value at both ends of the rod, and that at some initial instant the temperature distribution in the rod is known and given by some function f of x. These assumptions correspond to two boundary conditions at x equals 0 and x equals L, along with an initial condition at t equals 0. Let's analyze this system and see if we can determine a unique solution corresponding to the initial condition f of x. Solution of the 1D heat equation proceeds easily by separation of variables. Again, we have three types of solutions corresponding to the values of some constant lambda. Only the third of these options, given as a cosine term and sine term in x, and exponential in t, presents a non-trivial solution while satisfying the zero boundary conditions. Due to the boundary conditions, we are left with only the sine term, and the parameter alpha must be equal to n pi over L, where n is a non-zero natural number. We then have a family of solutions corresponding to the natural numbers n, each with an associated constant coefficient. We then apply the initial condition to see if we can determine a unique solution. We see that if f of x is some arbitrary function, we cannot fix the constant an to make the initial condition hold. However, recall that the heat equation is a linear partial differential equation. This means that we can add together linear combinations of as many solutions as we want, even infinitely many, and the result will still be a solution of the heat equation. Then the coefficients of our infinite series of sine terms can be determined so that a Fourier series converges to the initial condition function f of x. It is worth noting that this is exactly the kind of problem that Fourier invented the Fourier series for in the first place, although he was dealing with the heat equation in two spatial dimensions. We will get to that in later lectures. The astute viewer may immediately ask the following question. What if the function f of x is not an odd function? How can we approximate it with only a sine series? Turns out that you can make any function odd over an interval by inverting it over the y-axis, as shown here. In this problem, we are only concerned with the domain in x from 0 to L. If we define a function f odd equal to f on the interval from 0 to L and negative f from negative L to 0, we have an odd function that can be approximated with a sine series. Furthermore, the multiplication of two odd functions, like f odd and our sine term, is always an even function. So the Fourier coefficients can be calculated as twice the integral of the function f and the sine term taken over the interval from 0 to L. We have therefore achieved a unique solution to our initial and boundary value problem, making use of the sine Fourier series. The solution is an infinite sum, and the coefficients can be calculated explicitly for any initial temperature distribution f of x. Let's take a look at a quick example. Assume that initially the rod is at a constant temperature T0 across its length. The Fourier coefficients an can then be calculated. The constant function can be taken outside, and the result comes from integrating the sine term from 0 to L. Here's the result. I will leave it as an exercise to calculate the integral on your own. Good. Are you finished? We then have an explicit solution, given as an infinite sum of terms corresponding to our constant initial temperature. In practice, we can approximate the resulting temperature field throughout time by taking some large but finite number of terms of our series. Here are some resulting temperature curves plotted from the first 1,000 terms of our solution series. For this example, I have set all the model parameters equal to 1. The top blue curve represents the constant temperature distribution at t equals 0. Each subsequent curve is the temperature state at a time increment of delta t equal to 0.01 from the curve above it. Heat always flows from hotter regions to cooler regions. In this bar, the zero boundary conditions indicate that any heat inside the region will flow outwards. Therefore, the uniformly heated bar begins to cool off, with regions closer to its edges cooling faster than those farther away from the boundary. I hope you enjoyed this discussion of the heat equation. Stay warm and stay tuned for more content.